Hello everyone and welcome to Lecture Today. Today we're going to be talking about a very interesting, powerful procedure known as Liapunovs2ndMethod, and this will then lead us to a theorem called LaSalle's Invariance theorem. And both of these ideas, specifically Liapunovs2ndMethod, involves the finding of a very special function called the Lyapunov function for the differential equation system that we're considering. This is a technique that's specifically for analyzing the stability of nonlinear systems that is very, very, very powerful and can be applied both to physical systems and non-physical systems as well. So starting out, I'll start with some history behind this. In Liapunov's original work, (1892) work, he proposed two methods for testing stability. The first method is based on an infinite series solution to the ODE system. It's a powerful method. However, the second method, sometimes called Liapunov's direct method, is more direct and going to be what we're talking about today. And it's primarily due the goal is to find a helper function called a Lyapunov function. For physical systems like the pendulum problem and any other physical system that you can think of, this is typically related to the energy function of the system, the total energy. However, we can define the Lyapunov function for general systems as well, and finding it is not always easy or trivial, but assuming we can find a Lyapunov function, this can definitely help us analyze the stability of the system itself. And to give us some motivation, we want to remember and recall the multivariable chain rule for a given function v. So let's say that we have, first off, a differential equation, or the initial value problem. Psi prime is equal to some vector function of xi, where xi at t naught is equal to xi naught. And we'll denote this system, first order ODE system, as star. And consider what happens if we have a function, multivariable function of Rn, that's scalar valued. and it is continuously differentiable. And consider what happens when we take the derivative, the t derivative of v, where all of the variables I depend on t. This is the t derivative of the composition of the function v on the curve psi of t, which is a solution to our differential equation. Well, the multivariable chain rule says that v depends on xi1, xi2, xi3, all the way up to and including xi n, and all of these through the differential equation depend on t. So the multivariable chain rule then, this is going to be dv dxi1 evaluated at the point xi of t times xi1 dot plus dv dxi2 evaluated on the curve xi of t times the derivative of xi2 all the way up to and including the derivative of v with respect to xi n on the curve xi of t times xi n dot, which, as we saw before in the last lecture, we can simplify this as the gradient vector of v evaluated at the point xi of t and the vector dot product of this gradient vector with the vector xi dot of t. Or if you want to use primes, prime might be a nice, better notation to really indicate the derivative. This is the same thing as the gradient of the dot product with xi prime of t. And because xi prime satisfies the differential equation, this is the same thing as the gradient of v at xi of t dot product with the vector function g evaluated at xi of t. So this relationship right here, the multivariable chain rule, is essentially the basis for everything that we're going to be considering today. And specifically, this, if you recall from your multivariable calculus course, can be rewritten as well. We'll use this a little bit later on. This is the same thing as the magnitude of the gradient of v at xi of t times the magnitude of xi prime times cosine of theta, where this is a function of t. Theta is changing as a function of t. Theta here is the angle between the gradient vector at any point and xi at any point. But this angle right here is characterizing the sign of this v prime right here, the rate of change of v, which means, right, that we're going to be able to really see how this affects the solution itself. We can use this idea. If we can find a suitably chosen v, we can say definitively certain things about how the solution is behaving based on the vector field G. And to this end, we want to remember some basic properties about the gradient vector field from multivariable calculus. If we have this property that I'm about to write down holds for any vector function, but this picture right here will be just in 2D to illustrate what we're talking about. For a function, a gradient vector at a point xi always points in the direction of maximum increase in the function v at the point. And this means that we can actually show, we can prove that this is perpendicular to the level surfaces of the function v. So in 2D, that means that if you draw the level curves of a function and you have a local minimum of the function, the gradient vector will always be pointing outwards, away from the local minimum, perpendicular to the level surfaces, which in this case are level curves in 2D of the function itself. This picture corresponds to a local minimum of our function at this point right here. Also note that the vector xi prime for a given orbit, which is g of xi, always points in the direction tangent to the orbit. So if we have some orbit of our differential equation, I'll draw two separate unstable spirals here. At any point, the vector g is going to be tangent to the orbit at that point. This is just a picture illustrating that property. And this is what we've seen so far when we've been investigating solutions to differential equation systems. So let's make some definitions and then write down some the big theorems that are we're essentially getting from these two properties. Let psi star be an equilibrium point of the differential equation system star, and suppose that we can find a continuously differentiable function with the following properties. And this type of function we call a Lyapunov function. It has to be defined on an open set U that contains the equilibrium point. We call it a Lyapunov function for the system star on U, provided that the following three things are true. For points in U. V at the equilibrium point has to be equal to 0. V has to be greater than 0. Points xi that are not equal to xi star. This means that xi star has to be a local minimum of the Lyapunov function on U, and the third thing that we have to have, and the most critical, which is related to the property that I was talking about before, is that the gradient of V at xi dot product with G of xi has to be less than or equal to 0. So if we can, for a given system of differential equations, can find a function V that satisfies these three properties, we call it a Lyapunov function. And additionally, if the inequality in 3 is a strict inequality, meaning that the gradient of v at xi dotted with g of xi is strictly less than 0, then the function v is called a strict Lyapunov function. And the idea is that just a typo here and fix that. The spelling was off there. So the idea here is that due to the property that we just showed right here from the multivariable chain rule, these three conditions are actually going to tell us a lot about the behavior of solutions around this equilibrium point. So much so that we get a very strong theorem that we can immediately write down. This is sometimes called Liapunovs stability theorem. If v is a Lyapunov function for a star on an open set U, containing an equilibrium point xi star then xi star is stable. And furthermore, if v is a strict Lyapunov function, then the critical point xi star, the equilibrium point xi star, is asymptotically stable. And I'll go through and prove the first part of this. Both of these are in our book, but I'll prove the first one. The second one's a little bit more involved. But before I go through and prove these, I'll write down the basic geometric idea here in 2D. And that is that if you have an equilibrium point like this, and Lyapunov function, where we'll color this all green, and this should be the gradient of V. So all of these arrows are the gradient of the Lyapunov function. We can say something very immediate about how the solution is going to behave from the assumptions. So we know that from the multivariable chain rule, V prime is equal to the gradient of V dotted with G, and this means that the magnitude, or V prime, is equal to the magnitude of the gradient vector at any solution curve psi of t times the magnitude of the vector G of psi of t times cosine of theta of t, where theta is the angle between the solution vector, or the tangent vector to the solution, and the gradient vector. And from the third condition, if this is less than or equal to 0, that means that cosine of theta of t has to be less than or equal to 0. Which means that theta of t is between pi over 2 and pi. This is the angle between the gradient vector and psi of t. So then if this is a local minimum, we know the gradient vector is always pointing away, and that necessarily means that the solution has to either be perpendicular to the gradient vector or at an angle less, or at an angle greater than pi over 2. So it can't point in any of the direction of the positive increase in V. It always has to point in the direction of decreasing V. So then if you have a local minimum of V, you expect that your solutions will either stably rotate around the equilibrium point in the case of a normal Liapunov functions, non-strict. In the case of a strict Liapunov function, this forces them to actually converge to the equilibrium point. This is a very, very neat idea because it's directly related to multivariable calculus, and it can be applied in any number of dimensions. So we'll go through and do a proof of part 1. Like I mentioned, the proof of both parts are in the book. Let V be a Liapunov function for star on an open set U containing star because he was open, we can find a small enough region or ball around the point xi star. So choose the radius of the ball r sufficiently small so that the ball around xi star is contained entirely inside U, and to find the following value. Define M to be the minimum of the Lyapunov function on the boundary of this open ball. And note that because of the assumptions placed on the Lyapunov function, that M has to be a positive value. Because the Lyapunov function is positive on the set U. And to find set W to be the intersection of the set of points such that the Lyapunov function is less than m over 2 intersected with the ball that we previously considered. W is an open set and it contains xi star, because xi star is in this set by definition, and this is the intersection of an open set with another open set. Xi star is in this set because v of xi star is 0 by definition. So because of that, we can choose another ball, an S ball, to be sufficiently small so that the ball around xi star of radius S is entirely contained within this new set W. So W is some new set, and we can choose a ball of radius S around this point. That guarantees that this ball is entirely open, it's an open ball entirely contained in W. And then we have definitively then that if xi is in the S ball around xi star, then V of xi will be less than m over 2, and V dot, or V prime, which is the gradient of V xi of t dot xi prime, is less than or equal to 0. So V is decreasing. So for solutions, that are star, we denote it as a function of t with initial condition xi naught, where xi naught is in this ball, this S ball. V of xi of t xi naught will be less than m over 2 as long as xi of t xi naught remains in W. Which, as long as, because V is decreasing, we have exactly this. And what this means is that xi of t xi naught cannot intersect the boundary of the original R ball for t positive, which means the solution must remain inside this R ball for t greater than or equal to 0. Oh, and this should be xi star right here. And this is exactly the definition of stability. So xi star is a stable equilibrium point. And like I said, this proof and the proof of part 2 is in the Kelly book in chapter 3. Part 2 is done using the semigroup property, and it's a little bit more involved, but this is a nice proof, I think, of going through and showing that the first property holds, and the second property is relatively straightforward as well. But the idea now is that we want to kind of take this and look at a couple different examples. We'll consider the damped nonlinear pendulum from the previous class, because this is a physical example that is very important to understand, and also it gives us an idea of what's often a very convenient Liapunov function to look at. If we have a physical system involving the energy of the system, you can very nicely characterize the Liapunov function, or approximately what form the Lyapunov function should take. So recall that this is the system xi dot is equal to omega and negative r omega minus g over L sine theta. And recall that the equilibrium points are when omega is 0 and theta is n pi, where n equals 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. And we want to figure out how to choose a Lyapunov function. And for physical systems, we're going to try and use the energy, the total energy, to determine the Lyapunov function. For non-physical systems, so like purely mathematical systems, mathematical examples, or maybe for systems that don't have a clear, that are their application systems, they don't have a clear energy function. We have to be a little bit more careful, and it's a little bit more unclear on how to do that. But for physical systems, we can often look at the variation of the energy of the system. Which is really nice. So specifically for this system, if we try the function v of xi to be v of theta omega equal to 1/2 omega squared plus g over L times 1 minus cosine theta, we see that something really cool happens. The gradient of v in this case with a vector dv d theta dv d omega, which is going to be g over L sine theta and just omega. So that the gradient of v dotted with xi prime, which is g of xi, is going to be equal to this times this plus omega times this times this. In which we get a cancellation where we distribute this omega through and subtract we get this cancels with this, and so we're left with the gradient of our Lyapunov function dotted with g of xi is equal to negative r times omega squared, which is actually strictly less than 0. R is a positive constant, and omega, as long as omega is non-zero, this is strictly less than 0. But this will always be less than or equal to 0. Now, it's important to point out that this is only a Lyapunov function for the even values of n, specifically when n is 0, plus or minus 2, plus or minus 4, so on and so forth. V of xi star n is going to be equal to 0 squared over 2 plus g over L times 1 minus cosine of n pi, which is equal to 0 for even values of n. And for odd values of n, we don't get as lucky. But this has a physical reason as well. This is equal to 0 squared over 2 plus g over L times 1 minus cosine of n theta, right, n pi, which is 2g over L. So it violates the first condition here for the odd integers n. But this guarantees for us that these equilibrium points for the even values of n are in fact going to be at least stable. But we have a little bit of an issue here because w could equal 0, in which case this is if w equals 0, this value right here is equal to 0. So this only guarantees for us stability. Because of the fact that this, when omega is 0, is equal to 0. This is not a strict Lyapunov function. And this is sometimes an issue that will hopefully will resolve by the end of the lecture today, because we do know that these points for this example function, this example system of differential equations, because of the damping term here, are asymptotically stable. If we open up and take a look at, from the previous lecture, the simulation, where we showed from the simulation and we proved using linearization that these even values of n are giving us asymptotically stable critical points. It's right here. Right here, right here, and right here. So the problem here is that this function is 0. The Lyapunov function that we've chosen is 0 at these points when w itself is equal to 0, or omega itself is equal to 0. And we want to get the result of asymptotic stability here. So we'll see how to deal with this a little bit later on in the lecture. And the next example that I want to cover is an example that could definitely be applied in a lot of different ways, but right now we'll just write it down as a direct system. We'll say psi prime is equal to x prime y prime, which is negative x minus x y squared, negative y plus 3xy squared, or x squared y, sorry. Where if you go through and you solve for the critical points or the equilibrium points of this function, I will note that xi star is the point 0, 0 is the only equilibrium point. And a good question to ask is, how do we find a Lyapunov function for a system like this? And I want to emphasize here that it's not trivial and it's not always the same. Right? It depends heavily on the g function. So different g's are going to give you very different Lyapunov functions. However, for this one, we note that we have both quadratic functions of our variables, x squared and y squared, and we have a quadratic term in each one of these and a linear term in each one of these. And we note that if you choose function b of x, y of the form ax squared plus by squared the gradient of v is going to be 2ax and 2by. And the idea then is to take a function in this form, take the gradient, and we take the dot product with g, hopefully get some simplification that'll simplify to either a strictly negative function or just less than or equal to 0 with a proper choice of a and b. And sure enough, this is what happens exactly. So, taking the gradient of the function v dot product with g, this becomes 2ax times negative x minus xy squared plus 2by times negative y plus 3x squared y. Which simplifies to negative 2ax squared negative 2ax squared y squared minus 2b y squared plus 3 times 2, so 6 be x squared y squared. And a choice then of a equal to 3 and b equal to 1 will cancel the higher order quadratic term. So this term right here gets canceled with this term right here, and what's left over is that the dot product of the gradient in G simplifies to -2 times 3x squared plus 2y squared. Which for any value of x and y, this is always going to be positive, and therefore this is going to be strictly less than 0 for all x, y not equal to the critical point xi star. So by the stability theorem, the critical point 0, 0 is asymptotically stable. And sure enough, if we do a phase plane plot of solutions to this ODE, this is exactly what we see. The solutions very, very quickly, regardless of the initial condition, converge to this point right here. This is a very, very neat example. And the next example is going to be an entire class of functions. This is sometimes called the class of potential functions. So, where that xi prime is g of xi, if the vector field g of xi is what's called conservative, basically means that g of xi is equal to negative the gradient of some potential function, some scalar potential function, or some function psi of xi with continuous partial derivatives then the equilibrium points of star are the same as the critical points of the function psi of xi1 to xi n. because you'll remember from your multivariable calculus class that the critical points of a multivariable function are where the gradient vector of that function is equal to 0, or d phi d psi 1 is equal to 0 all the way up to d phi d psi n is equal to 0. So all of the partial derivatives that are simultaneously equal to 0. And so what we can say then is that if xi star is a critical point, and if the function psi has a local minimum, at psi star, then the function b of psi is equal to psi minus psi at the critical point. This function is a Liapunov function. For star. And this is relatively straightforward to go through and show. The gradient of v at the point psi dotted with g is going to be the same thing as the gradient of psi dot product with negative the gradient of psi, which is negative magnitude of gradient of psi squared, which this will always be positive, negative times positive is always negative. This will always be less than 0. So for a really good example of this, we'll look at psi is equal to 2D example, x times y times e to the negative x squared minus y squared, where if we take partial derivatives and look at the differential equation, dx dt is equal to d psi dx, which is negative y times 1 minus 2x squared times e to the negative x squared minus y squared, and dy dt is equal to d psi dy, which ends up being negative d psi dy, negative d psi dx, ends up being negative x times 1 minus 2y squared times e to the negative x squared minus y squared. We can go through and figure out the critical points of this function right here, or the equilibrium points of this system of differential equations right here. And this is a function that I use pretty heavily in the multivariable calc class. But there ends up being 5 equilibrium points where if you make the notation L is equal to 1 over the square root of 2, these 5 equilibrium points end up being 0, 0, negative L, positive L, positive L, negative L, positive L, and positive L, negative L. Not only that, but using the second derivative test from multivariable calculus, gives you a classification for each one of these points. 0, 0 ends up classifying as a saddle point of the function psi. Negative L, and LL is a local max of this function. And negative LL and L negative L are both local mins of this function. So by this example right here in our Liapunovs stability theorem, the function psi of xy minus psi at the critical point is a Lyapunov function. It's actually a strict Lyapunov function for these 2 points right here. And so these 2 points, the 2 local mins, are going to be asymptotically stable. And I'm not going to go through and calculate these zeros. It's a good exercise to go through and do. But this is just a 3D plot showing and verifying for you that L, L right here is the local max. Negative L is the local max. And negative L positive L is a local min right here. And L negative L is also local min. So when solving the differential equation, we expect both these 2 points to be asymptotically stable. And sure enough, if we run our Python code and go through and check this, this is exactly what we see. And I'll do that right now and bring the plot over onto the note sheet. Not only that, but the trajectory of the solutions seems very much to follow along with the behavior of this function psi, where we classified this point as a saddle point. These 2 points were local maxes, and these 2 points are local mins of our function psi. These are the asymptotically stable equilibrium points. All of the solutions are directly converging to these points, which is very, very neat. So we'll move on to apply and cover some more definitions that are going to be very useful to us in our next lecture, as well as for the last thing that I want to talk about. The set S in Rn is said to be positively invariant for differential equation star if for each initial condition in S the solution xi of t starting with initial condition xi naught is also in S for t in some set 0 to omega. In addition to this, we'll say that the omega limit set, the forward limit set for an orbit with right maximal interval of existence from 0 to infinity, is the set of points in Rn such that there is a sequence Tk going to infinity, the positive boundary point of the right maximal interval of existence, such that the solution at these times goes to the point eta. As k goes to infinity. Likewise, we define the alpha limit set in the exact same way, only for the left interval of existence for the orbit. So you can think of it for a given orbit, the limit set is the set of points that are converged to in either the positive time direction or the negative time direction. And these sets are going to be very important a little bit later on when we discuss limit cycles. But what we can go through and prove, this is done in the book, is a slightly stronger theorem than before, or I should say a slightly weaker theorem, because it applies to more general cases. If v is a Lyapunov function for star on a bounded open set U, then for any constant C, greater than 0, such that the set of points eta in U, such that V of eta is less than or equal to C is closed. This set is positively invariant. So we go back for a second to not this example, but the example prior. This example right here, we ended up showing that this was the Lyapunov function with a equal to 3. This is a Lyapunov function and b equal to 1 for this system of differential equations. So the positively invariant sets then for this Lyapunov function are the ellipses, or the sets satisfying v of xy, which which is 3x squared plus y squared is less than or equal to c. And these sets are ellipses that depend on C. But the sets of the form of points x, y, such that 3x squared plus y squared is less than or equal to C, because these are closed sets. These are positively invariant sets for this system. Like I said, the proof of this is in the book. But this definition allows us to greatly go through and actually come up with a better theorem that allows us to address the problem that we had in using Lyapunov functions for the pendulum example. This is called the LaSalle Invariance Theorem. And again, we have let V be a Lyapunov function for the differential equation system star on a bounded open set U containing an equilibrium point xi star if C is greater than 0 is a constant such that set S is a set of points eta such that V of eta is less than C if the set is a closed set in Rn and there is no initial condition in S for which the Lyapunov function, the solution is constant on the orbit starting at that initial condition. Then for all eta in S, the solution xi of t starting at xi naught, or starting at eta I should say, converges to the critical point, the equilibrium point xi star, as t goes to infinity. And the proof of this uses limit sets from before and positively invariant sets. And it's a little bit long, so I'm not going to cover it, but again, it's in the book. But the main way that we can use this theorem and what it's showing is that this theorem shows that under the right conditions, the existence of a Lyapunov function implies that solutions in a certain set must converge to an equilibrium point. In this theorem, the Lyapunov function does not have to be strict. So this is actually going to resolve the problem that we came up with before when we were investigating the stability of the critical points of the pendulum problem. This last statement right here makes this a weaker theorem, but it makes it better for us and better to use in general. It's more useful because it requires less assumptions on the Lyapunov function. So in the pendulum example, if we go back to this example right here, we had a problem where the Lyapunov function is constant. It's 0 on this line right here and on this line right here, which makes it not a strict Lyapunov function, yet the point is still asymptotically stable. So this LaSalle invariance theorem rectifies this problem, and we can see that by looking at the following. The orbits of this differential equation, or I should say on any orbit of this differential equation, the solution is never going to be constantly equal to 0. It's only equal to 0 when we cross the W axis here, the omega axis. This is the omega axis, and this is the theta axis. So for any orbit, you kind of follow any one of these orbits, the solution is never constantly 0, and therefore we can go through and directly apply the LaSalle invariance theorem to the solutions here. Furthermore, if we take a look at how the Lyapunov function is behaving with respect to these critical points, where the Lyapunov function that we had was y squared over 2 plus g over L times 1 minus cosine of x. These are the level curves of this function. The gradient is going to be perpendicular to the level curves and pointing away in the direction of increase of the function. So if we look at the regions where v of xy is less than s. These regions correspond to exactly the regions that are surrounding all of the stable critical points. And we can bring, for this example, s all the way up to 2 for the separatrix of these level curves. And even if you change the values of g and l, these regions are going to change, they're going to shift, but the idea is that for various values of g and l, physically speaking on Earth, g would be 9.8, l is the length of the bar, or the rod of the pendulum. We're seeing that these regions are characterizing from the Liapunov function by LaSalle's theorem these stable points of this system of ODEs. So this is a very, very neat idea and a very, very neat method that I think has been fully described. And the next lecture that we'll go over is the next topic that we'll cover is getting a better understanding of limit cycles, and when we can determine whether a system of differential equations is going to have limit cycles in the solution, and how to better understand them. But thank you very much for tuning into lecture today. I hope you had a great day.